This is a short video demonstration of a desktop process unit being used in automatic mode for the first time. In review, I have a loop controller here, which is monitoring the speed of a motor. We have a motor and a DC generator coupled to it. As the motor spins, the generator spins, makes a voltage, the controller reads that voltage, and from that interprets the speed of the motor. It's able to control the speed of the motor by sending a 4 to 20 milliamp output signal to a variable speed motor drive circuit, which sends a pulse width modulated power pulse to the motor driving at different speeds. So we have a self-contained control system here, a process which is the motor speed itself, and the controller here. We're going to demonstrate operation in automatic mode. First, I'm going to start this up in manual mode. We have the controller set for manual mode, as indicated by the red telltale light. The display says V for valve, which means the output signal in this particular model of controller. I'm going to dial up the output until I get the motor to spin, until we overcome friction. There, we're spinning. And you can see right here in the bar graphs, I'm pretty close to 50%. I'm going to try to achieve 50% in manual mode. It's going to dial the output up until the bar graph reads about 50. And I can even watch this in more detail by hitting the D button for display and toggle the display to my process variable. So here I see my process variable is 47.3%. If I go back to output again and adjust it up a little bit more, I can switch to process variable. I'm now at 49%. I can move the output up just a little bit more. Now I'm about 50% for my process variable. So let's say that I want this motor to run at 50% speed. Well, at this point, I've got it running in manual mode. If I were to load down the motor with my finger, the controller takes no corrective action whatsoever. It's in manual mode, so it will ignore any changes in the process variable. It will display what the process is, but it will take no effort to correct it or to maintain it at set point. At this point, however, I can put it into automatic mode, and now in automatic mode, it's going to try to maintain a set point right now of 49.78%. And if I try loading the motor down, it will actually take corrective action. First, I want to show you how this will respond to a change in set point. Watch what happens when I turn the knob with the digital display in set point mode. You'll see the set point go up, and you'll see the process variable follow along and then oscillate. You can even hear the motor oscillate. I'll put the camera closer to the motor and you can hear it again. You can see the oscillation in the bar graph when I go up and when I go down. In automatic mode, I make a set point change, which makes the set point bar graph rise or fall. The process variable bar graph then oscillates afterwards, and the output oscillates as well as the controller attempts to stabilize the process variable at set point. The reason it's oscillating is because I have too much gain programmed into the controller. Simply put, the controller is too aggressive. I can change the gain value, observe what it is right now, by flipping down this little doorway and pushing the tune button. When I push the tune button, the display changes and it says PG for proportional or gain. And right now the default value for the stock factory configuration is a gain of 1. So we have too much gain right now, and I can change that if I want and demonstrate how this will affect the control of the process. I'm going to take this gain value and adjust it down, let's say to 0.7 or so. I'm not going to be real particular about the exact value here. I'm simply doing approximate tuning anyway. So I'll adjust it from 1 down to about 0.7. I must hit the store button at this point to save that value. As soon as I save that value, now that new value becomes active. If I hit the exit button, and I go back to my set point display, I can adjust set point. And you'll notice when I adjust set point, there's a little bit of oscillation in the process variable, not nearly as much as what we had before. There still is some, though, and so if I were dissatisfied with that level of oscillation, I can decrease the gain even more. Let's do that. I'll bring the gain down to about 0.4, and I'll store that value. Now I can go exit out of that display, go back to set point. I'll raise the set point. You'll notice the motor speed does jump up without oscillating. However, now we have quite a bit of offset right here. Notice the amount of offset between set point and process variable. We're not exactly matching set point as we would desire to be. And that's a direct function of having lowered the gain. By lowering the gain value, we make it less aggressive, which means there's less tendency to oscillate. However, there's also less tendency to move the output to the point where it matches set point, and so we see a greater offset. Watch what happens as I go back to around 50% and I change my gain back to its former value of 1. So now I jump the gain up. Whoops, I went too far there. 0.9, 0.98, 0.994, 996. I'm awfully close. There we go. 1.0. And I can store that gain value. Now I'm going to exit out of this, and at this point I'll adjust my set point. Notice my motor's back to oscillating again because the gain is much more aggressive, but also notice how it follows set point much closer. There's a lot less offset than we had before. Let me adjust it up. We still see some oscillations, and there's a little bit of offset here between set point and process variable, but not nearly as much as we had before with the lower gain. I can adjust the gain up even further if I wish. Go back to my tuning button. Let's say I move the gain up to, let's say, 1.6, and I store that value. Well, at this point, if I make a set point change, well, we can see right here, the loop became unstable without me even making a set point change at all. We have so much gain in the system now, it completely overreacts and is unable to hold the process variable at set point or even hold it steady at any value. This is a very poorly tuned control loop. So to stabilize this, I can go back and change my gain. Let's say we go to a value like 1.1, and I'll store that. I'll store that gain value. You can see immediately the loop tends to settle out. There's something else we could have done to stabilize that as well. If I move the gain back up, let's say around 1.6 where it was before, store that. It starts to go unstable. Another way I could stabilize that is simply switch to manual mode. Oops, I have to get out of this menu first. I can simply switch to manual mode. Of course, when I switch to manual mode, my output becomes locked at its last value. So if I happen to press that button at the exact moment the output was at 0, well, that's where I'm stuck and my motor stops running altogether. Conversely, if I had hit the auto manual button at the point where the output was saturated high, I would have been left with the motor running full speed. So you got to be kind of careful to stabilize a loop by jumping into manual mode. It's often quite a bit better to stabilize a loop by switching your gain back to a lower value. That's a quick demonstration of the effects of the proportional or gain setting on the stability of a loop, like a motor speed control.